Atomic structure 2.
Oh, that's my chair squeaking. Uh, the essential idea here is the electron configuration of an atom can be deduced from its atomic number. Developments in scientific research follow improvements in apparatus, which makes sense obviously. If you have an apparatus which reveals new information, you then take that information and you can come up with new theories. And then the older theories are superseded. Um, for example, quantum mechanics is the most recent or current model of the atom. And these theories explain natural phenomena. Um, there is something kind of weird though about our understanding of atoms now and small particles, in that a bloke called Heisenberg, he discovered that we can never know the momentum and the position of a particle at any given moment. It's not possible. It's impossible. And that's worth taking a think about. So we might have all these fantastic models, but part of the model is that we don't actually know where a particular particle is at any specific time. Or if we did, we wouldn't know its momentum. Okay, there's a bunch of starter activities here which you're going to do. So work through these slides and the equipment's all laid out for you. Press pause, and when you finish, you come back to the presentation. You can press pause, obviously, and when you finish, come back to it. Okay, the Rutherford model of a nuclear atom. Nuclear atom. It doesn't explain the observations you've seen. You've seen these thin lines by the spectroscope. There's no reason why Rutherford's model would produce these. So, this new evidence has given us some new information, and we need to have a revised model of the atom. And this is just the nature of science. Like I said before, new scientific apparatus gives us new information. This new information needs to be thought about, and new theories are developed to explain natural phenomena. The old theories are superseded. The Rutherford model, it had a nucleus in the middle there, and you had electrons around the outside. Remember the alpha particles came in and were deflected from the nucleus. That's how he discovered, or how he came up with this model. We know the atom is mostly empty space, because the alpha particles, when Rutherford did his experiment, passed straight through like this. Just like that. The nucleus is very small and positively charged, so when the positive alpha particles came flying in, they bounced off. And the electrons are found in the region around the nucleus. What theoretical challenge is presented by this model though? Can you just think of anything here that would suggest that it would emit light at just specific energy levels? Not only that, if these electrons are all negative and the nucleus is positive, then wouldn't the electrons move towards the nucleus in a spiral, because the negative and positives must attract? If you look at this, it's a picture you've probably seen before, and it's the it's the old rabbit duck face. I mean, it's a face, I guess, right? It's both, depending how you look upon it. And the theory of knowledge connection here is that when you get a big paradigm shift in how something's perceived or how we look at something, the rules change. With the old model, where the electrons could be anywhere, We didn't need a whole new way of thinking. As soon as we found out that the specific lines being made, we needed to find, we needed a new theory, and quantum physics came into play. What did Niels Bohr, who came up with this, say to Wolfgang Pauli? Well, he said that we're all agreed that your theory is crazy. The question which divides us is whether it is crazy enough to have a chance of being correct. My own feeling is that it is not crazy enough, and quantum theory sure is crazy. To address the question of why electrons do not spiral in the nucleus, Niels Bohr proposed that the energy of electrons in an atom is quantized. What does that mean? It means that electrons are only allowed to have certain defined or discrete values of energy. Therefore, electrons may only exist in defined energy levels around the nucleus. They won't spiral into the nucleus. So this one here and this one here stay in this energy level. They don't slowly spiral inwards. Okay, and the same goes for these four on the outside. A good analogy for quantized electrons is the use of disembodied legs from below the knee. You can see here that the disembodied legs below the knee are standing exactly on the step, and these disembodied legs below the knee with the nice red shoes are standing exactly on a step. They're different levels, potential energy levels in this case. Here, the owner of said shoes is between the two levels. This is not possible, okay? For quantized objects, you can only exist or remain at specified levels. So, the experimental or empirical evidence Bohr used was something similar to this. He had hydrogen gas, passed electricity through it, which emitted light. This light he then separated out using something like a prism, and he got individual single lines which had wavelengths between 400 nanometers and 700 nanometers. He called this atomic emission spectra. And you'd be very happy to know that the electromagnetic radiation that you learned about in grade 10, and remember as if it were just yesterday, is returning. Let's have a look. We've got gamma rays, X-rays, UV, infrared, there actually should be micro there, and radio waves. As you go from gamma up to radio waves, the wavelength gets bigger, but the energy gets smaller. So the energy is bigger, and it says it at the top there, this away. Gamma rays have more energy than radio waves, and that's how the Hulk got turned into the Hulk, gamma rays. If you'd been hit with radio waves, he would have just been listening to music. Of course, that isn't true. Here, this teeny section there is what we can see. We can't see ultraviolet and we can't see infrared, but we can see this visible light. The cones and rods in our retina, back of our eyes, pick up light. And I can't remember which is which. One of the two differentiates between colours or wavelengths. Here, at 400 nanometers, we have violet. So this is at a higher energy level than the red over here, which is at a lower energy level. But the red has a longer wavelength. I remember that violet is more energetic by thinking of violent. Ultraviolet is more energetic. You need to know these. You need to have a very good idea and kind of memorize the areas of the visible light. So, to repeat, violet light, short wavelength, high energy. Oops. Red light, long wavelength, low energy. Did I say high energy over here? I think I did. Violet light, short wavelength, high energy. red light, long wavelength, low energy. So, spectroscopes. A spectroscope is used to analyze the light emitted from a substance. It disperses incoming light into its component wavelengths. In this way, you may think of the spectroscope as acting like a prism. When we view white light, viewed in a spectroscope, and I'm going to draw a torch there. That's the most excellent torch. If that was beaming white light through a prism, and there's the most excellent prism, you would see the rainbow, a beautiful, beautiful rainbow. If you were to do the same with neon light, you wouldn't see a full rainbow. You'd see individual lines like so. So we've got two types of visible spectra. We've got the continuous spectrum. A light source that produces a continuous spectrum suggests that the source emits all energies of visible light. All energies, all wavelengths. And an emission line spectra, a light source that produces a line spectrum, suggests the source emits only certain discrete energies of visible light, only specific wavelengths. So specific wavelengths at specific energies. So this is a discontinuous or line spectrum. That's what we know it as, discontinuous or line spectrum. Here we have a QR code, okay? If you use your phone and follow that, you'll get a fantastic atomic emission spectrum animation of what's going on. But I will of course go through it too. So, what have we got? We have what look like two electrons sitting in the ground state at the lowest energy level. Okay? They're stable. They're at the lowest energy level. If energy comes in, it could be from like light coming in can do it, or electricity, like when the electric arc that pushed the hydrogen electrons up. So energy comes in, it boosts the electrons to a higher level. Here they're being boosted to N3. And they've got to move up to a higher energy level because they've been given more energy. When they're up here, they're considered to be an excited state. It's an excited state atom, and it is unstable. It doesn't really want, I'm being metaphorical, but they want to get back down to N1. And so they do, they can drop back down. And you can see it's gone from N3 back down to N1. When it does this, it emits some energy in the form of electromagnetic radiation. But it could also have fallen from N3 to N2. Look, you can see it's a slightly smaller arrow. Electrons fall down to lower energy levels and they release light with different energy values. They release electromagnetic radiation or light with different energy values. And as you probably guessed, this distance from here to here being smaller, when an electron falls from one to the other, it emits less energy than when it falls a greater amount. So this one has more energy. Again, here's a QR code, and this one is worth taking a look at too. You think you need to have a video player that's flash enabled for it to work. I had to download Real Player for this to work. So let's have a look at the formation of the line spectra in hydrogen. In visible light spectrum, the stuff that we can see, the electrons always are falling back to N2, okay, to N equals 2. So we can see electrons falling from a higher level if they stop at N equals 2. The first one we can see is from N equals 6 to N equals 2. You see we've got some violet light, and it's just above 400 nanometers in wavelength. Next, we've got some blue light from N equals 5 to N equals 2. and that's somewhere between 400 and 500. Then we've got green light from n equals 4 to n equals 2. And finally, we've got red light, n equals 3 to n equals 2. And that is pretty near 700 nanometers. Okay, so this is why we get the 4 lines. Those 4 drops in energy from electrons moving from a high level to n equals 2, to the n equals 2 energy level. Okay, see if you can colour in this. What numbers should you put here? What units? What 4 lines? And then try and answer these questions. Press pause. Okay, so let's have a look. Well, first of all, you can put your numbers in, 400 to 700, and remember to put nanometers. And we saw we got violet, blue, green and red on the previous picture, and I'm just going to stick those 4 lines in. Okay, so that's what you want to look like. That's what you would draw. To which energy levels do electrons fall in visible light? And I hope you can remember, because it was only about 2 minutes ago. They fall to n equals 2. Which electron transition gives the red line? Is it the biggest drop or the smallest drop? Can you remember? Let's sneak back and have a look. It was the smallest one, wasn't it? It was n equals 3 to n equals 2. So, n equals 3 to n equals 2. So, which electron transition gives the blue line? Well, you can kind of work it out. If this was n3 to n2, this must be n4 to n2, this must be n5 to n2, right? Let's just check if I'm right. Hooray, I am right. And if we wanted to write a comparison, if we wanted to compare the energy of these 2 electron transitions, the red and the blue, what would we say? What would be important to say? Well, it's important to say that the blue emission has higher energy. The fact it's blue means it has a different wavelength. But you need to remember that lower wavelengths have higher energy. Why is there no yellow line in this spectrum? What do you reckon? If we go back, how far back was it? It's like here, I think. Nope. Even further back. You can see violet here, and yellow comes about there, right? So we've got red, and then you go through the yellow, you got a bit of green here, we had our blue, we had our violet, right? So the yellow here would need to come between the red one and the green one. Now we head back over here. Where were we? We were here, roughly there. Nope. This is the one. Why is there no yellow line in this emission spectra? Let me have a look. Let's just scooch back a bit. If we've got red, green, blue and violet, let's go back and have a look. We've got red. I need a different colour, don't I? That's not going to work. That'll do. We've got red here, green, blue and violet. Okay, we've got this kind of gap here, haven't we? And so it's this yellow that's missing. So it would come between the red, and it would come between the red and green. Sorry. So let's go back over here. And so we've got the red and green here, and there's no line there. Now we know, if we think about the disembodied steps, that the electrons can't exist between energy levels. Now if you remember, the red energy level was from N3 to N2. The green was N4 to N2. So there'd have to be another energy level here for a yellow one. And obviously there's no energy level there, so you can't, or you don't end up with an energy level here. Okay, so there's no, I guess, 3.5 N to 2N energy level. That should say 3.5. That should say N equals 3.5 to N equals 2 energy levels. So, there are 3 series of atomic emission spectra for hydrogen, and they are as follows. We've got these ones in the middle, and you can probably guess what they are. These are the ones we can see because they finish at N2. They're called the Balmer series, and they are visible. The electron falls to N equal 2. Next, we have these ones here. Notice they're dropping not as far, so you can probably guess that there's less energy involved, and you'd be right. This is called the Paschen series, and this emits light in the infrared series. Electrons are falling at N equals 3. And finally, we have the Lyman series, ultraviolet. Electrons fall to N1, and you can see they're dropping a much further distance. Okay, and ultraviolet light has far higher energy. Okay, which makes sense. Okay, so if we were to ask these questions with reference to the last slide, and we were asked to compare the energy of lines in the Lyman series and the Paschen series, what would we say if we're going to compare the energy of the Lyman series to the Paschen series? Well, you can see that the Lyman series they're dropping a long way. The electrons are dropping a greater energy difference. In the Paschen series, they're dropping a much shorter energy distance. So the energy levels are closer together in the Paschen series. They're further apart in the Lyman series. That makes sense, right? And there you have it. The lines representing the energy levels in the Paschen series are closer together than those in the Lyman series. Next. Oops, I don't want you to see that yet. Explain the difference in the energy released in the Lyman series and the Paschen series. Again, this just wants you to explain the energy released, and so you would talk about the distance between the energy levels. There's a far greater energy difference here than there is over here. Let's have a look what I wrote. Electrons fall to N1 in the Lyman series. So you've mentioned the actual energy level they're falling to. And it produces ultraviolet electromagnetic radiation with a higher energy than that of the Paschen series. The Paschen series produces infrared as the electrons fall to N equals 3. Splendid.